So in the last video we talked about the discrete maximum principle, which was given by this formula in here. Okay, and in this principle we were saying that that if we look to the mesh that I already drew before, okay, each approximated value at a given point at a time t equal n plus 1 is between the minimal value obtained at t equal n for all the x's and the maximal value between all these xj's. Okay, it's bounded by the ones before, and these ones are bounded by the one before, and etc. So finally I'm bounded between the minimal value and the maximal value obtained for t equals to 0. Okay, this is the discrete maximum principle. And now so I talked about this in the last video, and then I will now try to write in a matrix form the equation in order to write down a more general class of algorithms. So if we want to write the explicit scheme in the matrix form, if u now is the vector given by all the xj's, and then accordingly f is the vector given by all the f's with respect to the xj's, then in here we have the explicit approximation of the derivative of u with respect to time, and here we have this explicit approximation in time, and this will be the discretized form of our equation. Okay, then if we do so, the matrix in here should be the matrix that will give the approximation of the second derivative. So it should be the matrix given by 1 minus 2 1, because those were the coefficients in the approximation of the second derivative. Okay, so to write this like this, a and f are given by what's in here. So this is a and this is f. Try to write it element by element so you can understand how it works. And if on the other hand we write an implicit scheme for the time, then our equation will be written like this. With the implicit scheme, you go back to the implicit scheme in time written in the beginning of this part. So if we write an implicit scheme, we'll have this. And now, instead of doing the explicit alone and the implicit alone, we will try to write a combined form which contains a parameter theta, which is multiplied by this kappa a over delta x squared, and a 1 minus theta in here multiplied by the same parameter kappa times a over delta x squared, which means that we are doing a combination between both schemes. For this, in this combination, if theta is equal to 0, then what? Then we have a completely explicit scheme, and if theta is equals to 1, we have a completely implicit scheme. And if theta is neither 0 nor 1, but it's between 0 and 1, it means that our scheme is somehow a mix between both schemes. Okay, so if we write this again in the scalar form, we will have this kind of equations. Okay, of course, if theta is equal to 0, again we will have an explicit scheme as we had before, and if theta is equals to is not equals to 0, it's equal to 1, we have the implicit scheme. So for this kind of schemes, we write the consistency error given in here. So it's the same consistency error in before, but we have the theta that's a new parameter in this equation. To calculate the consistency error, we will proceed as before. So we'll be calculating the Taylor expansion. So in the first expression, we calculate the Taylor expansion of utn plus 1 xj, and in this case also of utn xj for a time step of delta t over 2. We calculate both, we obtain the result. I'm going fast because I want you to do it yourselves. Okay, so again we calculate the Taylor expansion in the space variable. So in the space variable, it's in here. this is the expression that you want to approximate or to estimate. So we can create the Taylor expansion and you obtain this kind of results. And then if you combine all the terms together, you will finish up by this kind of results. Okay, I went fast in here because I want you to do it. So I want you to do this proof alone to prove that the consistency error in this case is bounded by this term, which is second order in time, second order in space, plus a term first order in time multiplied by the 1 minus 2 theta. So it depends what's the choice of theta to know what order are we dealing with. Okay, so this is about this chapter. Hope it's all clear, and we'll see you in next videos.